Welcome back to class. Today we will go through the topic of multi-agent systems. Last lesson, we have covered the evolution from single agents that solve a task to a group of agents that forms a workflow to solve a more complex task. So when we call a tool, we can directly programmatically invoke the tool, and then the tool will perform its function and give us a response. For instance, if we are calling the model, we can create an instance of the OpenAI object from the SDK, and then we use the chat.complete.create function to get a response by calling its API. If we want to consume a tool, we can write in the system message to ask the model to give us a specific format. For instance, it starts with a capital letter function followed by the function and the arguments. And then we write Python codes to check if this capital letter function would exist in the response. If so, we will call eval function to evaluate the actual function call. And this function call points to the actual code that sits in the same program. So this is a very simple example of how we invoke function programmatically within the same internal system. But in a larger scope, not all the tools are sitting within the same code base. And also, it doesn't make sense for us to write all tools under the sun. For instance, if we want to access files from external storage like Dropbox or Google Drive, or if we want to access code from GitHub, or we want to access chat from Slack and knowledge from Wiki or some wireframes or drawing from Figma, we are not supposed to write all of these tools on our own in our same code base, and then we integrate them, invoke functions to call them directly, right? So it makes more sense for us to just integrate with them to some methods. So now let's look at this integration. Such integrations are mainly through API calls. So all of these providers will give us a set of API, or some of them may give us their SDK so that we can put all those in the code and invoke them directly. But this has a problem. So the problem is that there is an integration bottleneck. So imagine we are building a single agent and then we are integrating with all these 6 tools. We will need to integrate 6 times. And another system that needs to integrate with these tools, they will also integrate another 6 times. And yet another system to integrate. The integration takes M number of systems to be integrated with tools. And as a result, there will be M times N number of integrations, which is highly inefficient. Also, when we implement this in production, all these may come with limited set of technologies. Like for instance, GitHub SDK may come with Python wrapper without JavaScript wrapper. And then maybe Slack can only come with a JavaScript wrapper and Postgres can only give us a Go wrapper. So when we integrate, we cannot just use a single code base or a single language. We will need to also handle cross-language integration. And when we integrate, the API standards are not necessarily the same. The protocols used for the interface is not necessarily the same, so it triggers a lot of productivity overheads. Also, another problem will be authentication. So every tools requires us to create an API key or create some credentials. And all these credentials will be scattered across, say, the .env file. And if we have multiple repositories for our system, and these .env files will be scattered across many repositories. And also, when we build a system, we have a dev, we have a staging, and we then have a production environment. So there will be many environment files or environment configurations that we need to sync. This is also very challenging for a small team to keep it. Finally, there will be also context lost. When an agent switches tools, it often loses the states of the connection. So if there are multiple agents that is dealing with multiple tools in multi-turn conversations, the earlier conversations or the earlier productions tends to get forgotten along the process, which makes the later conversation less effective. A typical solution to this kind of problem is to set a standardized protocol and everyone follows. A protocol is a set of rules that governs the conduct of a procedure or the format of data. So one of the most well-known protocol is USB. So USB, on one hand, it connects to all these host or plug devices like a laptop or desktop. On the other end, it connects to the receptacle devices such as mouse, keyboards, webcam, or other devices that supports the USB protocol. And we don't need to build any integration between the computer and all these devices. As long as they fulfill the USB protocol, we can just plug one end to the computer and plug the other end to the devices, and then they will just sync or install, and then it will work. So now we will introduce this protocol for agentic tooling. So this is the notion of Model Context Protocol, or MCP. So MCP is the Model Context Protocol, and it has since become the golden standards for agentic applications since November 2024, introduced by Anthropic, which is the inventor of Claude. Looking at the diagram, so MCP works very similarly to USB. On one end, we have all the hosts, the application like the Claude desktop or Claude Code, or some programming IDEs like VS Code. So all these are the hosts. And then on the other end, there are the tools like the devices, like say PostgreSQL or Git or Slack, Google Map, etc. So if we plug one end to the computers and then we plug the other end to the devices, they will just communicate to each other because both end has developed interfaces that is according to this standard protocol. So here are some MCP design principles. So first, it's designed to simplify the entire integration process. So if the agentic systems and the tools are all developed according to the protocol, to integrate that for each agent, we just need to install and then for each, we can just develop according to the protocol. So after all this is done, we can just simply plug to the agent. And as a result, the number of times we need to integrate are reduced from m times n earlier to m plus n, where is the number of agents and n is the number of tools. It also allows flexibility, such as supporting various use cases. So here for a single agent, if let's say we want to retrieve some information from Wiki and then do some processing internally and then push it to Google Drive, that can be supported. Another agent potentially may want to pull some information from Figma and then write some code and then push it to GitHub. So this protocol allows complex workflow that can be defined by the client, and it can support many use cases that require pre-definition. Lastly, this protocol allows extensibility. We no longer to build all the tools to enhance its capability. We can simply adopt the MCP protocol, and whichever capability, we can just integrate the MCP servers or the tools outside of the agent to extend its capabilities. Even if there is no such MCP server, but if there is SDK or API, a developer can simply build MCP server like a layer that's in interface with the existing tools to provide capability for the agents to extend. Lastly, MCP standards allows agents from different systems to work with each other. So it's not system dependent, it's not language dependent. So it's very interoperable. It's like HTTP, where we can just use a browser and then we can access all the websites, whether it's written in Python framework or whether it's written in JavaScript framework. One of the very important features of MCP is that it comes with built-in security design. And this security design follows the following principles. So first, the security boundaries are set at the protocol layer. So on the left side, the agents are the MCP hosts. And on the right side, the tools are the MCP servers. These MCP protocols clearly separates the roles and responsibilities of the host and server so that they don't mess with each other. They can set their own security policies to be enforced when they are integrating with each other. So with clear separation between hosts and servers, security policies can be enforced at the protocol level itself. On the tool side, each MCP server can restrict which files or data it can return, regardless of what AI models request. And it follows the principle of least privilege. That means each of these tools or MCP servers should always expose the minimum capabilities that is necessary to support certain tasks. Say for GitHub, if you are the GitHub developers, you only want agents to have read access to the code base. You do not have to expose write or delete capabilities to other agents through this MCP server that you create. Next, MCP follows the zero trust model. That means among the agents and the tools, they don't have predefined trust to each other. There isn't a privilege for certain tools to give access to certain agents. All assumes no implicit trust. Finally, when we integrate our agents with all those tools, the agents will always request permission from the users. And when the user grants permissions, the agent will then execute the consumption of the tools to perform certain safe or dangerous tasks. And it's the user's jobs to ensure that the agent does not consume harmful tools or radically change things that results in irreversible outcome. So in summary, MCP comes with built-in defense in depth. There are many security layers that work together, and even one input validation fail, the resource limitations can prevent large damage. Okay, so now let's take a look at the MCP components. The MCP component starts with the host. The host is the application environments like cloud desktop that we may be familiar. So for the cloud desktop, we built independent MCP clients that is to be used to connect to MCP servers in a one-to-one relationship. Each MCP client will create a one-to-one relationship. So if we integrate with 10 MCP servers, there will be 10 MCP clients set up within the MCP host environment. And the MCP server will then communicate with the actual third-party services through the desired or the available protocols. Say Figma allows communication through in REST protocol, then the MCP servers for Figma will then communicate with the Figma services through HTTPS. The MCP communication flow works like this. So first, the MCP host will establish a connection to its MCP clients, and then the MCP server will be triggered and exchanged capability with the necessary tools. Once this connection is established, the clients will then request tools or resources through the MCP server. After the tools performed the task and the result is ready, the MCP server will then return the results back to the MCP clients. And finally, we will notify the actual service through pushing the updates. So MCP protocol relies on the transport layer. There are two types of communication in the transport layer. One is the standard I/O or STDIO. It's best used for local communication or desktop server. That means your MCP host and your third-party services all in the same computer. And the other one is through HTTP and SSE, which is Internet Protocol. And this is suitable for remote server that sits over the internet, and they are servers used as web services. So this is much newer than this using STDIO. So these are the remote MCP servers that was introduced in just a few months ago. There are several MCP message types where we send over. So generally in the request, the messages are sent from the clients to the server. And typically there are two list requests, which gets all the available tools from the servers. And there is tools call request that's request to execute the functionality of a certain MCP server. There is also resources list, which lists down all the available resources, and resources read, which reads the available resources from the list. There is also bidirectional notification, where both sides update if there is any tools exchange or there is any resource being updated. Now let's take a look at the MCP server side. There are three primitive types of MCP servers. They are tools, resources, and prompts. Tools are essentially functions that the AI can execute, but they are external and is communicated through MCP. Resources are essentially data in different forms that the AI can access. And finally, prompts are some predefined prompt templates that the AI can access and use. Chrome or Google, there is send email tool that can be integrated with Gmail or other mail providers. And there is also query database function that can be integrated with database like PostgreSQL. The characteristics of MCP tools includes the following. So you will need to name the tools with clear and descriptive identifiers so that when the MCP clients broadcast the request and receive the description, the MCP clients is able to understand and choose the correct tools to call. You will also need to define input schema using JSON schema so that the standards agreed to standard format. When you return the result, you should return a structured result, typically in JSON or dictionary format or a list of JSON objects. You can also allow the MCP clients to perform some actions while it's consuming the tools that you're exposed to, such as API calls or file. It can also support for progress updates. And finally, you should handle errors with meaningful messages so that the requesting agents know what to do next. Okay, so this is an example of the definition of an MCP tool. So we see there's name such as get weather, and then the description of what this tool does. And then there's an input schema, which we request the MCP clients to send over. Next is the MCP resources. So MCP resources allows the MCP clients to request data from the remote location like file systems or database. And they are typically accessible through TAF. If it's a file, then it's file : / and the TAF to the file. And if it's a database, then it will be like a URI that is accessible through the HTTP protocol. And there are several typical resource types. So one is the text, which can be in documents or code files, or it can be MIME types, such as the plain text or JSON application. It can also be binary resources, such as files, like images or PDFs, or some archives that is 64 encoded. Finally, it can be dynamic resources, such as complex database queries or complex API responses. So this is a typical schema of MCP resource. So we see that there is the URI, which allows through this location. We will define the name, the description, and the type. The MCP clients can also request to subscribe to MCP resources, which keeps the data consumption live rather than a single request and then a single response. So first, the clients will request to subscribe to the resource through its URI, and then the servers will check the active subscription. When the resource changes, the server will notify, and the clients will receive the updates of the resources through the notification. And finally, the clients can reread the updated resources through the subscription. The last primitive type is MCP prompts. So prompts are essentially predefined templates for the requesting agents to interact with. Some prompts can be like summarize documents or generate code review. Essentially, the prompt templates comes with a name, the description, and the required arguments, which is very similar to consuming OpenAI API calls. Here are some best practices for building MCP servers. Basically, it's just like building any software programs. We want to have very clear naming, including the descriptive tools and resource names. We want to have very good descriptions. This is very important because the agents are going to consume the MCP servers through the description. And given a good descriptions, the agents can then be able to understand what the tools does and what is available. You want to have a strict schema and you want to validate all the inputs, such as the types, the validity, and the acceptable range. We want to have good error handling that covers not just the happy paths, but all the edge cases. We want to have a good logging that tracks all the operations. And if things fails, it's very easy for us to go and see what goes wrong. And finally, we want to maintain good versioning. So this helps us maintain compatibility and also maintainability. So now we will walk through one example of implementing an MCP server, which is to implement a web search tool. So this example is implemented in Python. Okay, so let's start. So first, we will start with setting up the server and list implementation. List tools is one of the functions that we allow the MCP clients to consume. So first, we will import from the MCP servers libraries for the servers, stdio server, and the tools and text context. We will instantiate a server called web search server into the app instance. And then we define an async function with the signature app.listTools on top. And then we simply returns the tool with the name search, description of search the web, and the input schema, such as the type properties and the required fields. After that, we will implement the call tool that contains the definition or the business logic of this particular tool. And we also write the main function that runs the app and allows the read and write access. That's all we need to build the MCP server. Next, to integrate with the MCP server on the client side or the host, say we use a cloud desktop, we can open up the MCP server configuration file, which is typically a JSON file. We can just simply add the Python server inside the MCP server field, and we put down the command Python, since it's written in Python, and the arguments. So when we actually consume the server that we use, it will call Python space -m space web search server to consume the MCP servers that we have just written. If we have other servers, like say some that is written in JavaScript, we can write it in here. And to consume it, it will use another server such as Node. In summary, MCP standardized agent tool integration, and there are three primitives MCP server types, such as tools, resources, and prompts. MCP follows the client-server architecture over two typical message protocols, such as standard I/O or HTTP. It uses JSON RPC 2.0 messaging protocol for the message schema. It comes with in-depth built-in security model. And it is the fastest growing ecosystem of community servers. Next, let's talk about agent-to-agent protocol, which is an higher order protocol if we compare that with MCP. So we have seen that the MCP protocol is a standardized protocol that enables agents to connect with external tools. For agent-to-agent protocol, it's also another protocol or an open standards that enables communication for an internet of agents or agents that is exposed over the internet rather than in an internal system. So think of it HTTP or HTTPS protocol for an internet of agents to communicate and discover each other. So now let's compare the difference between MCP and A2A. First, let's look at its purpose. So the purpose of MCP is to extend agents' capabilities, whereas the purpose of A2A is to enable collaboration. The model used for MCP is a client-server relationship where the client is typically a desktop or a web application and the server's tools that provide certain services. For A2A, it's typically peer-to-peer. So each agent wants to talk to the other agents and borrow the capabilities of the other agents, while your own agents can also be exposed to the internet and allow other agents to consume. The focus of MCP is on the tools and the resources, and the focus of A2A is more on accomplishing certain tasks together with extended help from the agents and also the messages that is passed among the agents. Next is the integration direction. So for MCP, it's more vertical integrations where it goes deeper into the tools. And for A2A, it's more horizontal. That is a flat or equal level importance among the communication of the agents. And the relationship analogy is different. For MCP, it's more like top-down, like from agents, which takes a higher position, and tools, which takes lower position. And for A2A, it's like its name suggests, agent to agent. So it's very peer-to-peer oriented. Why do we need A2A as a protocol? So A2A establishes effective communications with external agents that allows all these important functionalities. First and most importantly, agent discovery. This protocol allows us to identify the capabilities of other agents and let us find them to extend our abilities. And next, capability negotiation. We will be able to find out what can each agent do, task dedication, how to assign and track work, progress tracking, so how to monitor task status, and result sharing, how to exchange outputs. So with A2A, all this is by default achievable. Inside the A2A protocol, it's actually quite similar to MCP. So the standardized communication layer includes HTTP, server sends events or SSE, and the schema used for the message is JSON RPC. To establish the communication, the client's agents on the left here is responsible for asking for work. So essentially, what it does is to discover other agents, create tasks, send messages to request for task. And once the task is done, it will receive the results of the requested task. On the other hand, the server agents responsible for doing the work requested. So the server agents has its own agent cards that clearly describes what these agents can do and is willing to do. This server agent handles the requested tasks and processes the request from the client's agent. And in the end, it will return the results or the artifacts to the client's agent. Here, the summary of the key concepts. Agent cards, the metadata that describes what the agents can do or the agent's capabilities. Tasks that is requested by the client agents and received from the server agents is essentially the unit of works that is communicated and agreed between the agents. Message, the actual communications within a task. Parts, content units such as text, file, and data. Artifacts, the outputs produced by the task execution. And finally, push notifications, the async status updates between the agents. Agent cut looks something like this. It's in JSON format and it describes what the agent's identity is, its capabilities, and how to interact with them. This is oftentimes published at this URL known /agents.json. So we can see that there is the name, the description, the URL that can access the agent, the provider, the version capabilities, such as the functions that it can do, or the skills that we have, and of the authentication. In particular, the skills are a collection of various skills that we define in a list. So each skill will be another JSON object that has its ID, name, description, and the text and examples. So all these informations are part of the metadata of the agents that tells the requesting agents or the client's agents what these agents can do. There are multiple ways for the client's agents to obtain the agents cards from the agents in the wild. So the most straightforward way is to access the well-known URL through these conventional locations within the agents. Another way is through registry lookup. So there are some centralized agent registries that's built for reputable organizations like OpenAI, Anthropic, or some other organizations. It can be through referral. That means if the client's agent is already interacting with a server agent, the server agents can refer the client's agents to another agent by sending another agent's agent card to the client's agents. And finally, it can be manually configured. For instance, the user who have information about some agent's information, he or she can provide the agent's cards directly to the client's agent so the agent can have access to the agent's cards locally. To establish the communications, we will let the client's agents to discover the agents in the wild. Say, if the user requests to draw a horse, the client's agent will first search which agents can do the task. And once the client agents identify the server agents that is able to do the task, it will then assign the task to the agents through the A2A protocol. And the server agents, once received the task, it will process the task within itself and then updates the progress or the results of the task. And finally, send back the artifacts to the client's agents, which later return back to the user. This is very similar to the HTTPS protocol that we have been using to communicate via the REST standard. A task in A2A protocol represents a unit of work to be performed, which contains messages, states, and produced artifacts. So this is an example of the task in JSON format. So we see that there is the ID of the task, which is very important. This helps us identify the multi-turn conversations without explicitly including in the context, like how we consume an LLM model. We have the session ID, we have the status of the task, and the artifacts, which starts with empty. And when the task is done, it will contain the returning results and the metadata, such as the time creation of the task. These artifacts, once the task is done, will include the respective artifacts that can be a file, can be some text, and so on. So next, we will demonstrate one complete workflow of implementing an A2A server. Okay, so recall that the client agents and server agents model, where the client's agents sends a request to the server agents, and then the server agents perform the task and return the results. So now let's start with establishing the server agents. So just now for MCP demonstration, we use the Python implementation. So now we will use JavaScript to show the example. So first, we will create an app that is an instance of the Express server. Next, we will set up the function to handle the potential clients, agents request. So here we use a switch case statements that handles all the potential requests and the logic inside that is associated with the requested task. Given the switch case statements, it will trigger the right functions based on the request methods. And then we will write the actual functions to process the task. Now let's see how to implement the A2A client's agents. So here we will first create A2A client type. We will start with the discover agents, which fetch the available agents through the conventional URL. We will fetch the agents cut from the conventional URI, and then we have another function that sends the task to the desired server agents to perform. So this part is where we fetch the agents cut, and this part is how we send a task to the server agents. Similar to calling LLM models, in A2A client-server communications, we also have multi-turn conversations. However, we don't really need to put in all the task context in the API call. We can simply use the same task ID to indicate that this conversation is in the same conversation. So the A2A protocol will automatically sort this in the whole message to identify that this is a multi-turn conversation. With A2A, we can now instruct our local clients to orchestrate specialized remote servers agents for our request